So today we're going to talk about yet still another rotating force balance. This one may be probably the most famous force balance in like atmospheric and ocean sciences. And it's one of the most uh, central concepts in how all rotating fluids work. It's called geostrophy, which is a very fancy sounding word. Kind of like, uh, yeah, anyway, we'll get to what it means in a second. Um, so this is the last of our dynamical topics that really is covered in the Collins et al. Book. So if you haven't looked through chapter 3, look through that, and then we're going to come back and this at the end of today, you'll actually be able to also finish Wunsch chapter 3, and then we're on to talking about other chapters in Wunsch. So the reading will start to jump ahead. We'll start moving ahead again after today. And oops, sorry, I should have updated. The response is already due, so homework 2 is the next item on the agenda. Does anybody have any questions about homework 2 before we go on? More questions, I should say. Okay, I guess not. All right. So homework 2 is coming up, and that will be a good setup. It'll touch on some of the topics that we're going to touch on today, and it should get you set up for doing your plans document, which is going to be about gyres, wind-driven gyres, and Ekman, and all this sort of things. So you'll have or upwelling zones, and you'll have all of the tools that you'll need to do to start talking about that. So that will be um, coming up. All right. So today, we're going to review the Ekman force balance. Then we're going to review the hydrostatic force balance, and then we're going to, am I on the wrong slides? No, I just didn't update these at all. Ha! All right, this is not what we did today. This is what we did last time. But we are still going to start off by reviewing Ekman. And so Ekman is a good starting point because remember we said that Ekman is sort of this excess bit of velocity shear in the upper ocean. And that excess bit of velocity shear comes from the force balance between the wind and the Coriolis force. So the wind going this way, the Coriolis force going this way. In order to have the Coriolis force oppose the wind, you have to have the depth integrated transport over that layer be perpendicular to both the wind and the Coriolis force. So notice that the Coriolis force is to the right of the velocity direction by 90 degrees. We're going to use that again in just a second. So this is one balance, which is between this term, the Coriolis term, and the sort of external forcing or the friction term that's part of this external forcing term. We also can write this in a little bit more simple way if we want, where we can use this A cross B cross C equals back cab rule, which some of you might have seen from vector calculus. Basically, in this formula where we have F cross VE equals this friction force, we can cross it again with F, and then we get something of this form. So both A and B here would be Fs, and then C would be a VE. And so we just follow that formula. We get F times F dot VE minus VE F squared, which is equal to F cross the F cross F. We can then simplify that one again to solve for VE, because now we're in a simpler situation. Here, F dot VE is perpendicular to F, so this term goes away. So the only term we have is this VE F minus VE F squared, which goes on this side. We move the minus sign to the other side and move the F squared downstairs. And then just note that F is in the vertical, and we can write it like this. So this says that the Ekman transport, that is this arrow, is equal to the frictional force, the wind direction, crossed into Z, which is the vertical direction. So if you do the right-hand rule, with starting with your fingers in the wind direction and then go upward, you'll find that your thumb is always pointing in the Ekman transport direction. So that's consistent with this little force diagram. And if F was negative, like we were in the southern hemisphere, it would just be going in the other direction. It would flip the sign and it would go to the left of the wind rather than to the right of the wind. Any questions on that? Okay. So we can use almost the same, almost the same force diagram, but in place of the wind, we have the pressure gradient force, which pushes from high pressure to low pressure. Now, what's surprising about the geostrophic balance, this is the geostrophic balance right here, is that even though the force pushes from high pressure to low pressure, in order to balance that high pressure to low pressure against the Coriolis force, the geostrophic flow goes perpendicular to both the pressure gradient and the Coriolis force. So just like we had in the Ekman case, we had just a few terms in the balance. So in this case, it's the pressure gradient force balancing the Coriolis force, and the rest of the terms we're neglecting for this geostrophic balance. And now, when we go back to our diagram of like where in the column we think it might be, here's our Ekman flow. It's the excess up here in the surface layer. And then all of this essentially vertically uniform flow we could imagine to be geostrophic. The geostrophic balance occurs pretty much whenever you have a pressure gradient. The Coriolis force, at least at low Rossby number, the Coriolis force comes in to balance the pressure gradient with this kind of a force balance. So you could say if there was a line of high pressure and a line of low pressure, the geostrophic flow would be along the pressure surface. Or if there was a central area of high pressure, the geostrophic flow would be circling around that central line of high pressure. And we're going to see a lot of examples of this as we go. We're also going to take that pressure breakdown that we thought about with the gyres and see a little bit what this looks like in this case. We're going to do a lot of that in the next class. We can play the same, exactly the same game with the cross products that we did last time. And we go through, except here it's the geostrophic one that balances and the pressure gradient force. Oh, there should be a minus sign on this one. But anyway, this gives you this direction. So let's see if it works. Z hat crossed into the pressure gradient. So the pressure gradient actually pushes from low pressure to high pressure. So the pressure gradient goes from backwards to the pressure gradient force, which goes from high to low. The gradient itself goes from low to high. So Z hat cross pressure gradient is vertical crossed into this direction. So do that with your hand, with your right hand. Start with your fingers at Z hat, cross them over to the pressure gradient, and you'll see that your thumb is pointing in the direction of the geostrophic force. There's also an F in the downstairs, just like there was in the Coriolis force. So if we were in the southern hemisphere, we would expect the geostrophic flow to be to the left of the pressure gradient force rather than to the right of the pressure gradient force. We don't have any vertical integrals involved here at all. This force balance occurs layer by layer. There's no vertical connection between the layers, at least expressed in this part of the force balance. There will be a vertical connection between the layers because the hydrostatic pressure accumulates vertically the way we've been talking about all along. So this pressure doesn't come out of the blue, it comes from the hydrostatic pressure. And so there is a connection in the vertical, but this geostrophic balance, the pressure gradient, just balances the the Coriolis force and the geostrophic velocity happens at every vertical level. How do I know this is a horizontal balance rather than a vertical balance? Well, F is in the vertical, so F cross VG is something that's not in the vertical. So I can interpret this pressure gradient, the important part of it that's participating in this balance, as only being the horizontal part of the pressure gradient. The vertical pressure gradient has the hydrostatic balance, and this is for the horizontal part of the pressure gradient. So are there questions on any of this stuff? Are we ready to start looking at some cartoons?
I have a question on the Z direction. So is it pointing downward?
So in this picture, Z hat is pointing up at you out of the
Okay.
page. And
So
so
it's
we're looking
like
from above downward and it's coming up outward.
So Z
So
will be pointing up.
Z is pointing up. Z cross gradient of pressure, which is this confusing part is the pressure gradient force is negative gradient of pressure. So the gradient of pressure is in the opposite direction of this arrow.
Oh, okay.
Z is pointing up. Cross that gives you geostrophic flow.
Okay, gotcha. Thank you.
So if we compare between the Ekman one and this one, you can see that what happens is the Z is in the back in this case, and the Z is in the front in this case. That's because there's no minus sign here. There's no minus sign in front of the force here. So there's F cross Z, and then here it's Z cross grad because this does have a minus sign. And switching the order of things in a cross product reverses the sign. So that's why these two are a little different. Does that make sense to everybody? Okay. So let's do our normal review of balances. We've got a full momentum equation, which here, and rather than an external force, I put in a viscous force. We have viscosity, gravity, pressure gradient. What balances have we learned? Well, we've learned this one. Inertial oscillations will balance between the time rate of change and the Coriolis force. Everybody else neglected. In order to get there, you need this set of parameters to be basically everybody is small except for the temporal Rossby number, which is order 1. Here's the Ekman layer. So now the Ekman number is order 1 for this flow. The two Rossby numbers are small. And so that means that all of the terms in the equation will be negligible except for these two. Well, in the horizontal equation anyway. The hydrostatic balance is our only balance in the vertical, and it just balances the pressure gradient in the vertical to the gravity also in the vertical. And this tends to hold when the aspect ratio of the motion is small. So that's almost always the case for large scale ocean flows because just the ocean is wider than it is tall. The Taylor-Proudman theorem is a bit funny. It has part of the pressure gradient, the way we talked about last time. The part of the pressure gradient that depends on the density is left out of this balance, but the part of the pressure gradient where the pressure and density are co-varying is left in. We're going to come back to this in a minute because this term is active when we have so-called barotropic flows. And barotropic flows, this term will be the right one to think about. And in the barotropic flow, the Taylor-Proudman theorem still holds even when the density varies. So it involves the Coriolis force, the barotropic part of the pressure gradient, and the gravity. And now we have our new one, which is the geostrophic balance, which is simply the pressure gradient force, or its horizontal part, as we said, balanced by the Coriolis force. So at this point, every term in the equation has gotten into one of these balances, except for the advection term. And we're going to come back to the advection term in a minute. But in general, in this class, we're going to be thinking, at least with pencil and paper, about small advective Rossby number. And so this term is small. In the echo model, in our model, this term is not assumed to be small. It just is small because the flows are not that strong. And so this term down here of the flow speed over the Coriolis times the horizontal length scale, that still turns out to be a small number, which makes this term small in comparison to the Coriolis force. But you can check in the model whether geostrophy holds. Is geostrophy more important than the balance that also includes this term? That's something you could check. That's exactly the kind of things that would be good to check in this paper or the next paper. And we're going to see these force balances sort of play out in different parts of the flow field. So where does the pressure come from? Well, I just said it in words, but it comes from the hydrostatic balance. So the pressure at the sea surface accumulates in the vertical, and so the pressure is the weight above you per unit area, where the pressure at the starting point, whatever this top part of this integral is taken to be 0. So we don't consider the atmospheric pressure. You could get a little more fancy and put a P atmosphere there and maybe have it be varying, but that's more complicated than we need to. We know that in just 10 meters or so, we've overwhelmed the atmospheric pressure with the ocean pressure. So we're normally just thinking about the ocean pressure starting at 0 at the surface of the ocean and then accumulating as we go down. So if this is true, then everything just kind of accumulates coming down. So you could say, well, how could we change this? We could change this by changing the density. If it was more dense, the pressure would accumulate faster. Or you could change it by moving the sea surface up and down, which would change Z0 from place to place. We're going to see that both of those are important in thinking about geostrophy today. Okay, so here's our pillows and bricks imaginary gyre. And so we have a sea surface height anomaly where the pressure and the sea surface height goes up. The near surface pressure goes up in the middle of the gyre because this stack of pillows starts higher up than the stack of pillows to either side. And so there is pressure throughout this. But the densities is all pillows in this light surface layer. So we don't have a density change between them. So the pressure anomaly that happens right below the surface is going to be the same pressure anomaly here, the same pressure anomaly here. The pressure is going up in all three columns, but it's going up at the same rate. So let me show you what I mean in equations. So here's an ocean surface, which goes up and down. So this could be like the middle of our gyre, and these could be the edges, low versus high. And now I'm going to start using eta for the ocean surface variable, which is what it's called in the echo model. And it's a little simpler for me to write than Z0. So that's better. But what I mean is the height of the ocean surface, like where we start that pressure accumulating as we go down from the atmospheric pressure, which we're taking to be 0. So dp dz equals minus rho g. So if the density is constant, then this side of the equation is just a constant. So the pressure increases linearly from wherever it starts increasing, which is at the location of eta. So I've drawn for you isobars, that is, surfaces of constant pressure, and you'll see that I drew them to be the same shape as the sea surface height because this distance between this pressure level, 0, and whatever that is, say the 1, and pressure level 2, pressure level 3, is going to be exactly the same as the distance between pressure level 0 and 1, 2, 3 over here, and the same 0, 1, 2, 3 over here. So the pressure gradients in the horizontal, this high pressure under this sea surface height anomaly, is exactly the same at this lower depth, is exactly the same at this lower depth, is exactly the same at this lower depth. So it's just mapped over and over again, down and down. Another way to think about it is here's just the solution to this differential equation, this ODE, with constant rho naught. So P is just rho naught G times a linear function, which starts counting at eta and then increases linearly the deeper you go. So this whole formula depends on X and Y and Z, but eta only depends on X and Y, the horizontal location. So if I ask about the horizontal gradient of pressure, it doesn't see Z at all. There is no horizontal gradient in the Z term, so that drops out. So the horizontal gradient of pressure is just given by eta, the variations in eta, and we're going to use that a lot. So here we are. Here's our hydrostatic balance, just that rewriting those equations. So the Coriolis force on the geostrophic velocity is minus pressure gradient over rho naught, which if I take this formula and do that manipulation I just said, take its gradient, I just get G gradient of eta here. So the geostrophic flow is in balance with just the variations from horizontal variations of the sea surface height if the density is constant. And you can do the same game with that, move the F cross to the other side, and you get this formula. So now we're saying from low pressure to high pressure is from low sea surface height to high sea surface height. And the geostrophic flow goes perpendicular to that pressure gradient force, which is just totally due, in this case, to the sea surface height variations. Sea surface height variations here as well. Does that make sense to everybody? Okay. So we've got our geostrophic flow. It becomes this sea surface height version in constant density. We could go ahead and follow the rest of the steps in the Taylor-Proudman proof and find out that, hey, this thing right here, because this has no vertical derivative, and if I take the vertical derivative this side, the only thing that survives is v, dv dz is equal to 0. It's still Taylor-Proudman, even though there is this geostrophic flow field. So the geostrophic flow, at least in the constant density case, is in Taylor columns. So if we go back to our little movie, we have basically constant density water here because it's all room temperature essentially. There's a little density difference between the ink probably and the water, but let's not worry about that too much. And so remember, we had these sort of sheets or curtains of flow that flowed along like that. And now you might say, well, what's the velocity field that's actually driving these sheets to wrap up on themselves? It probably is a geostrophic flow. And so you can see this little spiraling pattern here probably has a low pressure at the center because it's an anticyclonic flow or against the rotation direction of the tank. Oh, wait, hold on. Which way is the tank rotating? The tank is rotating that way. Yes, still thumb up rotation rate. So all of these flows are still kind of driven by probably anomalies in the sea surface height here, the tank height from that parabola that would be motionless. And then when we zoom in, we can see that these inertial oscillations sort of superimposed on that. So we want to think a little bit about how the inertial oscillations and geostrophic velocities might work together. What if we have both present at the same time? Can we think about a simple force balance that takes care of that? And in fact, we can. Okay. But before we get there, let's just step back and think about this whole situation one more time, but let's make a more generous definition of what's going on with the density field. So we could suppose we allow the density to vary, but it can only vary as a function of the pressure. So these isobars that we drew before are also the isopycnals. So the density is getting higher as we go down, the pressure is getting higher as we go down, but they're getting higher in the same way so that there's a mapping. The density is just a function of the pressure. This condition right here is barotropic. That's the barotropic condition. Oceanographers like to get a little loose and then say things that are consequences of this relationship. But this relationship is what we really mean by barotropic. It means that the density is a function of pressure and nothing else. It's not a function of time. It's not a function of X and Y. It's not a function of salinity. It's not a function of anything else. That's all that it goes with. This doesn't happen very often in the oceans, but it's a useful simplification, and it's less simple than thinking that the entire ocean has constant density. Okay, so if we take this and then we take our hydrostatic balance and we solve it, we now get this rather ugly situation where our pressure is an integral from the sea surface height down to z of just a variable density. And we don't know anything about this variable density except that it is also a function of the pressure. So this is complicated because this is the pressure at one depth. This depends on the pressures at all of the depths from the surface down to where you are. So you might not think that this is going to get much simpler. Well, let's go ahead and plug it in. We can take the gradient of this thing. Fine, we take the gradient and we get this rather complicated formula, which says we accumulate the pressure from the surface down based on whatever the density is, and the gradient of that is the thing that drives the flow. And so this still doesn't look that simple, but we could ask questions like, is it still Taylor-Proudman at least? Do we still get variations below? And is it still the sea surface height variations that are driving this? You might think that it has to be the sea surface height variations that are driving it because this condition kind of says the density is inert. It just goes along with the pressure. So even though it's varying in the vertical, it's not, and with the pressure, it's not varying interestingly in the horizontal. Let's see how that goes if we try and prove the Taylor-Proudman theorem again. Okay, so here's our geostrophic condition with the barotropic density. We take the curl of that, like we did in the Taylor-Proudman proof, and we get curl of F cross V. That's just a complicated thing on this side. If we take the curl of this side, we get two terms. We get a term that's the curl of the density, the gradient of the density, crossed into the gradient of the pressure. Look at that thing. That's just a cross product between two different gradients. Well, we just said that the density is a function of the pressure alone. If that's true, then the density gradient and the pressure gradient have to point in the same direction. Let me say that again. The density is a function of the pressure alone, then the density gradient will just be the gradient of some function of pressure, which will be equal to the derivative of that function times the gradient of pressure. So it'll be proportional, it'll be in the same direction as the gradient of the pressure. Cross product between two things that are the same is zero. So we still get that the curl of the Coriolis force is zero because this cancels out in a barotropic fluid. And so we're back to our business where we have F cross gradient of F dotted into del of V is zero. So dV dz is zero. So not only constant density fluids, but barotropic fluids are still barotropic hydrostatic fluids are still in a condition where the geostrophic flow is in Taylor columns along the surface isobars. So that's really pretty interesting, and it doesn't shear below, even though all that density, all that crazy stuff is happening because of the magic cancellation here in the way that this term works out. It doesn't mean that we have any of those, we don't have anything interesting here. So when we read the high sea surface height and the low sea surface height as high pressure and low pressure in a barotropic fluid, we can consider that to go all the way down to as deep as it's barotropic. Now you might say, well, what is it if it's not barotropic? Well, it's not barotropic if it has some of this term. We call that a baroclinic fluid, and we're actually going to come to an example of baroclinicity in the fluid in just a second. But let's think back to our Ekman transport diagram. So our climatological winds are in the red, which forces Ekman flow, Ekman transport in the purple, which leads to low and high pressure zones where the Ekman transport either piles up or drains out the water. This is assuming that the piles aren't able to drain away, which is a kind of big assumption, but that's the way that it works out here. We'll talk about why that is later. But if the high pressure stay where the convergences are and the low pressure stay where the convergences are, then we actually have a sense of what the geostrophic flow should be like. The geostrophic flow around a low pressure center will go around and around the low. And in fact, it'll go around and around the low. It's just doing that backwards in this direction because it needs to go this way to have the high pressure outside to the low pressure, that pressure gradient force be balanced against the Coriolis force that's pushing out. So we're going to go counterclockwise, cyclonically, around low pressures, clockwise or anticyclonically around high pressures in the northern hemisphere. In the southern hemisphere, we're going to go counterclockwise, which is still cyclonically around high pressure, around, oops, sorry, just said it backwards. It's hard to keep this straight. We're going to go counterclockwise, which is anticyclonic in the southern hemisphere, and clockwise around the low pressures, which is cyclonic in the southern hemisphere. In fact, though, this low extends all the way along here, and this high is like that. So there's a pressure gradient force southward all the way around this reentrant Antarctic circumpolar current region. Which way does the geostrophic flow go in the Antarctic circumpolar current, given the fact that we're expecting high pressure to the north and low pressure to the south? Any guesses? There's only two guesses here. Eastward or westward? Nobody wants to take a 50-50 chance? All right, let's talk it through. Which way does the Coriolis force need to push in order to keep the high pressure from flowing into the low pressure to oppose the pressure gradient force? Does it need to push northward or southward?
Northward?
Yep, exactly. So which way does the velocity have to go for the Coriolis force to push northward? Remembering that in the southern hemisphere, the Coriolis force is to the left of the flow direction.
The velocity has to go east?
That's right, eastward. So, in fact, the velocity is going the same direction as the local winds. The Antarctic circumpolar current goes this way, around and around and around Antarctica, and it's going in the same direction as the winds, but not because the winds are pushing it sort of downstream. It's this complicated thing where the Ekman transport is adding pressure gradients, and then the pressure gradients are piling up in such a way that's pushing the flow to have a Coriolis force in balance, and there it goes. Another way to think of this is you could think of the entire Antarctic region as being a low pressure, and then say, well, a low pressure should have a cyclone going around it. And in the southern hemisphere, a cyclone would go around and around in this direction. So it's it's a cyclonic sense around all of Antarctica, or it's in such a sense to give you a northward pressure gradient that opposes this setup of the highs and lows from the Ekman transport. Does that make sense? So we're starting to get there that we actually can talk about big currents and surface currents and winds and pressure fields all together as part of the same conceptual framework, which is making good headway into how the large scale ocean currents work.
Taylor, can I
Mm-hmm.
ask a question? Because
Mm-hmm.
I think I might not have I got something wrong. I don't know. So
Sure.
from the previous slide, so I don't know why, but from the previous class, I thought the places that you have the high pressure systems in the atmosphere, you would have a low pressure system in the gyre. But no, they're like couple.
Yes, no. So I'm not actually talking about the high pressure. Those highs and lows are not atmospheric highs and lows. They're sea surface height highs and lows.
Okay. Because
Although
yeah, that's why I'm
you're
confused.
right on track that the atmospheric circulation above is also a high pressure system above where the sea surface height is high, and a
Okay.
low pressure system above where the sea surface height is low, which is why the winds are in the directions they're in. So
Okay.
they're kind of piling up on top of each other.
And
Um,
then you have this high because you have convergence in, yeah,
yes.
okay. Okay,
So we
now
call it
I got
high because there's Ekman convergence, and then the high pressures are under the high pressures, which makes the gyres turn the same direction as the winds turn. So they're going kind of downwind in all of the basins, but not for the reason you'd think, not because the wind is pushing them in the wind-driven direction. It's a lot
Okay.
more complicated than that.
Okay.
They could
Thank
go
you.
the other way. If you figured out a way, if the piles aren't able to drain away, imagine that the piles drained away faster than they accumulated. So you actually had low pressures piling up in these convergence zones and high pressures in the divergence zones. Then it would have go the opposite. The ocean circulation would go the opposite way, and it wouldn't care that it was going upwind, which is
Okay.
kind of a funny thing to think about.
Yeah. Thank you. Thank you.
Yep. Okay. So often people like to think about this in terms of like eddies or storm system scale. And so you can do that if there's a high pressure like this, just like we had a whole sort of gyre circulation that was going anticyclonically around a high pressure. If you just had one eddy that was the sea surface high, you'd have circulation this way, which is to get your fingers to curl around in that direction, you have to put your thumb into the page. So that means it's anticyclonic in the northern hemisphere to go clockwise. And then if you have a low pressure system, to get your fingers to curl around that way, you would have your thumb pointing out of the page. So there's cyclonic circulations around, which are counterclockwise in the northern hemisphere around the low. We can switch to the southern hemisphere by just reversing the slide. You can notice all of the words here are backwards. So this is the southern hemisphere by flipping it over. And now the sense of the circulation around the high is still anticyclonic, but anticyclonic is the opposite direction in the southern hemisphere. It's counterclockwise. Anticyclonic is clockwise in the northern hemisphere, counterclockwise. An anticyclone is always around a high pressure system in both hemispheres. Similarly, a cyclone is always around a low in both hemispheres, but a cyclone in the northern hemisphere is counterclockwise, and a cyclone in the southern hemisphere is clockwise. Okay, does that make sense to everybody? It takes a little while to get on the tip of your tongue which one flips as you go from hemisphere to hemisphere. So you can think about this more slowly as you try and figure out how these wind patterns as you review these slides and the different gyre patterns as we get into those. And just to, in the Collins book, there's a nice 3D visualization, which is kind of our pillows and bricks diagram, but just the pillows part at the top, saying if you have a raised sea surface, you'd have a pressure gradient force out, so a Coriolis force in, which you need to have a geostrophic current going this way to have the Coriolis force pointing in, at least in the northern hemisphere. So this one is kind of the side view of this one, if that makes sense to everybody. Okay, so now let's go back to our little pressure map here that we saw from the model results and look in more detail. So if the geostrophic flow flows along pressure contours like this, around a high, and along pressure contours like this, around a low, which way is it going here? It's flowing along the pressure contours. And this one is a high, so it's flowing anticyclonically, clockwise, around here. And then it's flowing the same way here. It's flowing the same way here. What's happening over here? Well, a bunch of pressure contours are all piling up against Indonesia and Japan, right? So this is the Kuroshio. It is the very intense piling up of pressure contours against the western side of the Pacific. And then it comes out and it sort of continues across the ocean like that. But parts of it are kind of recycling to go around and go again. Let's look at the subpolar gyre in the Pacific. It's going the opposite direction, following along these pressure surfaces. And it's piling up, maybe not as intensely, on the other side. And so this part comes in and joins in together with the Kuroshio. This current up here is called the Oyashio. and it's a southward current that comes and meets the Kuroshio at the Kuroshio extension where it separates off of Japan to head out into the Pacific. So the Kuroshio and Oyashio are the western boundary currents on the western side of the Pacific, where the pressure changes quickly from some background level up to the high value that it has in the center of the North Pacific subtropical and North Pacific subpolar gyres. If we jump over to the Atlantic, we see a similar kind of pattern. Here are some high pressures in the subtropical gyre of the North Atlantic, and they're all packed in on this side in the Gulf Stream. We recognize that's the Gulf Stream. It separates here at Cape Hatteras and heads offshore to go up here over towards Europe. There is a weaker Labrador current that comes down and matches up that's part of the subpolar gyre, which is going this direction, around and around and up into the Labrador Sea, and then down and along kind of down to about Maine, and then around again. So we're not only reading this pressure map as the evidence of where the Ekman transport is piling up, which is a consequence of the pressure patterns in the atmosphere above, but we can read it as the streamlines, the flow lines of these large ocean currents, at least the surface ones, because this is really the pattern of the pressure field in the near surface. And here's the roaring ACC, the world's largest current, and you can see how the pressure contours here are just many, many, many of them all the way across the Southern Ocean. And so it's going, as we figured out last time, eastward, just like around and around and around, going that way underneath the wind stresses, carrying carrying the currents around and around Antarctica. We can look at the South Pacific subtropical gyre, which is going the opposite direction. You know, this one is counterclockwise, this one is clockwise. They're both anticyclonic, but the direction of anticyclonic changes at the equator right here. So this one goes around, and so the East Australia current is one part of that gyre. Similarly, there's a Brazil current over here that's part of the subtropical southern Atlantic gyre, and then there's a subtropical Indian Ocean gyre, which goes kind of here over against Madagascar and goes back and forth like this, and actually kind of sneaks in here into the Somali current, which goes behind Madagascar down to the tip of South Africa, and then retroflex and kind of joins in with retroflex means to turn around quickly, turns around and kind of joins in with the ACC for a while. So basically, these patterns of pressure that we've been talking about, which are just as simple as where the Ekman transport converges and diverges, is really setting up the whole kind of flow pattern for all of the major currents, at least at the surface of the ocean all around the world. So it's just like the pillows pattern, and now we can pay attention to this, that the hill center is offset to the west. Yeah, it's really offset to the west. The hill center is somewhere over here, not in the middle of the Pacific, all the way over there. So it's right next to these western boundary currents. So if you look at this map, you say, wow, all of the big currents in the world, except for the ACC, are on the western side of the oceans. There must be some kind of physical explanation for that. We're going to get to that soon. Okay. Now let's talk a little bit about the baroclinicity. So there is baroclinicity here because the pillows turn into bricks in a way that is not just a function of the pressure, right? Remember, barotropic means the only thing that sets the density is the pressure level, which basically would mean that the height of the pillows was the same at all locations. But here, the height of the pillows is taller in the middle than it is on the sides. So the height of the tall stack of pillows and short stack of bricks means there's baroclinicity here at the picnic line. The depression of the picnic line is a baroclinic effect. Okay, so what does it do? If it's baroclinic, it means we don't have Taylor-Proudman anymore. So what does that mean that the current can do? We've talked about these current patterns at the surface, and they're going around and around and around and doing their thing. And we imagine that they continue to go down because the fluid is stiffened by rotation, at least if the density is barotropic. But what happens when the density gets baroclinic? What can happen then? Do we still have to have the no shear in the vertical direction? Anybody want to guess? Or say in an informed way? All right, no takers. Okay. So somebody come in and explain to me what's going on here in terms of the flow fields. We're below the picnic line. We're deep. The pressure gradients have largely vanished. What's the flow like?
It's solely driven by like salinity gradients, probably, mostly at least.
It could have a salinity gradient effect, but if it was going to drive a salinity current, it would need to have an impact on the pressure field, if at least if it was going to be geostrophic in the end. So pretty much all of the gyres have gone away by the time we get to this depth. The ACC is still there. It still has a westward flow. It's still a little bit lower pressure on this side than that side. It's fewer contours than before. So it's weaker than it was nearer to the surface, but it's still there at this depth. But all of that action, the Kuroshio has vanished. The Gulf Stream has vanished. The Brazil current, the East Australia current, all of those gyre circulations, they're all gone because since the density is baroclinic, we can have variations in the flow field in the vertical. So it's not Taylor columns all the way to the bottom of the ocean. It's only kind of Taylor columns up between the surface and the picnic line. Below the picnic line, most of those circulations have actually canceled out. Now, if we go a little bit deeper, we'll start to see things like the deep western boundary current, which will be a new pressure anomaly that comes up for different reasons at a deeper depth. But in this model anyway, at 1,500 meters, there's really just not a whole lot of circulation going on in any of the basins, except for the ACC, except for the Southern Ocean. Does that make sense to everybody? Because of baroclinicity, we can go from an active flow field at 5 meters depth to a very quiescent flow field at 1,500 meters depth.
Would you mind explaining one more time how that's a result of baroclinicity?
So we go back to the Taylor-Proudman theorem.
Yeah.
We say dV dz is 0 if this term vanishes. That term doesn't vanish if the flow is not barotropic. If the flow is baroclinic, which means not barotropic, so density is more interesting than just a function of pressure, this term will be something. And we don't know what that something is, but it means that we could have a velocity that changes in the vertical with depth as soon as we have the density doing something interesting. Now, it turns out that in our pillows and bricks, we do have a density surface that's doing something interesting. The picnic line is depressed underneath the sea surface highs because this stack of pillows is taller than this stack of pillows and this stack of pillows. So that means that the pressure gradients down here are going to be different than the pressure gradients in here. And the geostrophic flow that's in here going around and around this high may not be there, or maybe something totally different down here. Now, previously, we argued that the tall stack of pillows, this little extra bit of pillows might compensate for this little extra bit of bricks, or bricks versus pillows down here, in such a way that the pressure gradient below the picnic line might be weak in the horizontal. Because even though this is high, 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 when you get here, these start accumulating faster because they're denser. So they're high, sort of high, a little bit high, about the same from here to here to here. Does that make sense?
The only thing I'm not super clear on is why the difference in this pillow stack height indicates that pressures, or that the density is functioning more than pressure. Because before we said that it was fine, because there was
Right.
more on top.
So let's
Oh,
go back to
because it's more-
this figure. So here we are. These are more subtle than pillows and bricks, but this is in a barotropic ocean. I said that these are isobars, but
Yeah,
also isopycnals. So the densities are aligned with the pressures, right? So
okay,
wherever you have a high pressure, you also have a high density. Wherever you have a low pressure, you also have a low density. A surface-like density is a low density. A bottom-like density is a high density. Now let's go look at the pillows. We have a high pressure, a low pressure, but then we get down here and look, it's inverted. We have high density under low pressure, low density under high pressure. So it's not barotropic. It's baroclinic. The density here is not a function of pressure. Where the
yeah,
high pressure is, we have low density near the bottom, with the depressed picnic line. Where the low pressure is, with the elevated picnic line, we have high density.
great, thank you. That makes sense. The pigment line doesn't follow the surface elevation, so there must be
Exactly.
something else going on.
There's something else going on, and that something else is in such a way that it cancels the effect. So if you're accumulating as you go down, it might be that the pressure gradients at the bottom are really small, which is in fact what they are, at least in this model. So this idea had been kind of floating around, maybe not explained with pillows and bricks, for a long time. And so people, when they first started making ocean measurements, they couldn't measure the sea surface height very well. So they would assume a depth of no motion. And they would say, just 1,500 meters, let's just say there's no motion there. And then they would accumulate the pressures up from that and figure out what the sea surface height was doing based on observing the density structures. Now we actually can observe the sea surface height with GPS or from space directly. And so we don't have to make that level of no motion assumption. And you could say, like here, the level of no motion assumption would be kind of crummy because look, the pressure is actually pretty high in the Mediterranean. And so if you went up above the sill of the Mediterranean, there would be pressure gradient right there because of the different water masses. And the same between the Arctic and the Atlantic or across the Bering Strait. And obviously the ACC is still here. So there isn't a level where there would be no motion. There's just maybe locally you might have kind of a no motion condition, but really the important idea here is that baroclinicity changes things. In these big gyres, it tends to quiet them down as you get below the picnic line. But maybe they're not totally calm. Maybe this model is a little wrong, all those kind of things. That's exactly the kind of thing that we could look for in one of the gyre papers coming up. Does that make sense, everybody? Okay. So we're about to change, we're about to change pace and do something slightly different. So I want to make sure everybody is pretty squared away on what geostrophy is, right? Pressure gradient balancing Coriolis in such a way that the flow goes along the pressure surfaces like they were a flow field, at least in steady flow. And so you can just read the pressure maps, the maps of the contours of pressures as the flow field for the flow. And that's really helpful because if you have a map pressure field, it actually kind of gives you like the direction that flow is going. It goes cyclonic around low pressure, anticyclonic around high pressure, or kind of the equivalent of that. If you have just low pressure all along and high pressure all along, you can work out which way it's going by thinking about the pressure gradient trying to push southward, which means the Coriolis force needs to push northward, which means the flow needs to go eastward in order to have a northward Coriolis force to the left of the flow. Okay? Any other questions about geostrophy before we move on? Okay, cool. All right, so I said we had all the terms in the equation tied up except for the advective term in one or the other of these budgets. So if we just say small Rossby number, small advective Rossby number, and throw away that advection term, we have this term, the time tendency term, appearing in just one of our budgets. The Coriolis term appears in two of our budgets, but it appears in one for the Ekman velocity and one for the geostrophic velocity. And then we have the friction, which really only depends on the Ekman velocity because the friction is negligible outside of the Ekman layer. And the only shear that we have in the Ekman layer is due to the Ekman velocity, not due to the geostrophic velocity. Because as we argued, the shear in the Ekman layer, the geostrophic flow is going to tend to be kind of Taylor-Proudman and won't be very vertically sheared. So we can just replace this guy with the Ekman velocity. And then the geostrophic velocity is gobbling up whatever there is for the pressure gradient. So what happens if I just add these three velocities together like this? Inertial, Ekman, geostrophic. What if I just take all of them as my total velocity? Well, if I plug that total velocity into this term, what happens? If the Ekman flow is steady, right? Assuming that nothing is changing about like the friction coefficients or anything, or the winds, if the winds are steady. So there is no time derivative of the Ekman current. The geostrophic flow, assuming the pressure gradient is staying steady, like we're imagining with these large-scale maps, it's also steady. So there's no time derivative of that. So the only time derivative is of the inertial oscillation, which conveniently balances the inertial oscillation part of the Coriolis term. Well, there are two other parts of the Coriolis term, this one and this one, but this one conveniently balances the friction. And this one conveniently balances the pressure gradient. The gravity is in the vertical. All of these are horizontal processes. So these are horizontal momentum balances. So gravity is there in terms of setting up the pressure field, but it's not there in any of the horizontal balances. So if we have small advective Rossby number flow, taking inertial oscillations plus Ekman plus geostrophic, we've just explained the entire equation, all of the terms in that equation. We have a balance for each of them, and we have a name for the velocity that goes along with each one. And you might say, why am I allowed to add together different solutions? This is crazy. Well, you are, because this, once we've gotten rid of the advection term, is a linear partial differential equation. Well, except for this little nonlinearity here, which we're not talking at the moment about what goes on with density, but everybody else is a linear equation. They're linear in the velocities anyway. Linear in the velocity, proportional to the linear in the velocity, proportional to linear in the velocity, and linear in the velocity. And so you can use the principle of superposition, which is you can add together solutions to this whole equation set as long as they all are consistent with the boundary conditions and other pieces, and get another solution to the equation set. So we're kind of done in explaining the kinds of velocities we're going to get. We've gone through all the balances, and any term in this equation that's doing something interesting, we can think about a way to come up with a velocity that talks with it. And if you think back to our rotating tank case, which I'll go back to the little movie and play it again because we have a little bit of time. Well, now I've lost the movie. If you think back to the rotating tank video, oh, here it is. That's exactly what's going on here. There's a geostrophic flow. There's inertial oscillations, and we don't see it because these dies aren't at the very bottom, but there would also be an Ekman shear in a bottom frictional boundary layer as well. So the solution to the flow in this tank is just the sum of those three velocities. Now they're all really complicated and kind of turbulent, but that's all you really need to explain the majority of the flow field that's going on in this rotating tank. Those three types. Okay. So, what if it's not totally negligible advection term? Well, we could try and do exactly that same game, but keep this nonlinear term. And then each one of these budgets gets another term, which is proportional to kind of two velocities in it. Two velocities, two velocities. And so these are not linearly accumulating, so they're not equal to the advection term on the total velocity, because you've got all of these cross terms that are missing, that are on this in this, but not given by any of these. So if it is not small Rossby number, you cannot make this assumption. So this is why why all of our force balances we've been focusing on are small Rossby number, and why we're excluding our thinking for the time being about really large scale flow where the Rossby number is small, because that's the easy place to think about all of these different force balances, because you get a linear PDE. Does that make sense? Okay. So the last thing I want to do is show some little videos about a plug hole experiment. So if you have a tank and you open a plug in the middle, the fluid will go out the plug hole and down the bottom. And as it drains out, if the tank is rotating, which it could be if it's in a rotating tank, or if it's on a rotating planet, it should go one direction and not the other. Which way does it go? Well, there's low pressure in the middle because the surface is draining down toward the plug. Low pressure in the middle, high pressure on the sides. So what's it going to be? Cyclonic. So you can cause a cyclonic anomaly by pulling out a plug hole in the middle. So here is a lab experiment doing that in a rotating tank. This is, and you can see that the little floating discs are going cyclonically down the plug hole. Play that again. Cyclonically down the plug hole. They're kind of moving along the uniform pressure surfaces, which is what they've marked here with the grid. And then they have a small drift across those pressure surfaces. So the flow here is mostly geostrophic, and then there's a little bit of inward flow superimposed. Everybody get why I'm saying that that's geostrophic flow? Okay, what if we slow down the rotation tank rate of the tank? Now there's just a little bit of geostrophic flow, mostly just plug direct flow to the plug hole. So this is kind of the thing that you think is normally going to be the case in a moderate Rossby or large Rossby number fluid, but in a low Rossby number fluid, you get this fast rotation case, which means that things don't go out directly, they go around. So this is a fun Simpsons video, which I'll let play about this effect.
Water will only go the other way in the southern hemisphere. What the hell is the southern hemisphere? Oh, haven't you ever looked at your globe? See, the southern hemisphere is made up of everything below the equator. This line. So down there in, say, Argentina or Rand McNally, all their water runs backwards? Uh-huh. In fact, in Rand McNally, they wear hats on their feet and hamburgers eat people. Ooh. Which way does the water go in your toilet?
Just a minute, I'll check. Again, and I will translating for the El Presidente.
Which way does the water turn in your toilet?
Dice que el curso está cambiando. Ay, caramba. Los insurgentes ya van a capturar la capital. Necesito huir.
All right. Anyway, so this continues on until Bart finds an Australian kid who is willing to explain what's going on. You can watch the full video from the slides if you like. um, let's continue on. In the real world, you actually don't get as large of an effect. You don't get as large of an effect as that. And why is that? It's actually very, you have to be very careful to get it to always go cyclonically as it goes out the plug hole. Why do you think that is?
Because the scale is too small for Coriolis to apply.
Exactly. So pretty much when you flush the toilet, it's a large Rossby number event, not a small Rossby number event, because the flow down the plug hole is pretty fast compared to the rotation rate, which is just going around once per day or once per pendulum day, right? So there are lots of fakeries and all kinds of interesting things on this. You can go to these videos and check out in this Snopes debugging of this. One of these is talking about a tourist trap where in Kenya where these sort of charlatans take you across the equator and then show you that as they pull the plug hole, it goes different directions. But in fact, in the video that they have, they get it backwards, which direction it's going to go, because it doesn't really matter. They're sort of shaking the bowl as they pull the plug hole. So it's very easy to do what Bart was trying to do and stir it backwards with your hand. You can easily get the thing to go the other way by stirring it vigorously in the opposite direction and imprinting some sense of rotation opposite to the sense of rotation of the Earth. So you can go play with this the next time you take a bath. Okay. Last topic here. Let's talk a little bit about more about Bear Clinic in a sense that's maybe a little bit less complicated than the gyre case. So here is an example of barotropic densities on just a simple pressure gradient. So high pressure over here, it's tilting, lower pressure over here, same height of pillows, same height of pillows, same height of bricks, same height of bricks, parallel lines to the surface. This is a barotropic configuration. And so the pressure gradient here is the same at every depth. It's going from high pressure at this side to low pressure at that side. And it is just depends on depth. So the flow here is in Taylor-Proudman balance. The flow is always trying to push it back up, going that way. The flow is always out of the page at all depths here. Okay? We're looking from the side. Here's Z. What if we have just a stack of pillows next to a stack of bricks? The stack of pillows might start a little bit higher at the surface than the stack of bricks, which I haven't made obvious enough, but it is a little bit higher. So at the surface, we have high pressure on this side, low pressure on this side. And then at the bottom, we have high pressure on this side and low pressure on this side. Why do we have high pressure on this side?
Because it's more dense.
Exactly. The pressure is the weight of what's on top of you. So on the brick side, on the dense side, the pressure is going up faster than the pressure is going up on the pillow side. So we get down here at the bottom, and now the high pressure and low pressure are reversed. So we have two different directions of pressure gradient forces, from the left to the right at the top and from the right to the left at the bottom, which means that the geostrophic velocity is out of the page at the top and into the page at the bottom. So we have a vertical shear here. Is this a baroclinic or a barotropic condition?
Ferroclinic?
Baroclinic, exactly. Because the density is not a function of the pressure. The density is, in fact, sort of opposite of the pressure, where it's low pressure, there's high density, and high pressure, low density, but then it flips at the bottom. Now there's high pressure, high density, low pressure, low density. So there, the density is not a function of the pressure. So it's baroclinic, and it is sheared because it is baroclinic. So there's one more thing about geostrophy we want to learn, which is called the thermal wind relationship. And this is where you put geostrophy in the horizontal together with hydrostasy in the vertical. Under either barotropic or baroclinic conditions, it works for both, and it gives us the shear that we find. That's the deviation from the Taylor-Proudman flow. Let's see how it goes. Here's geostrophy. Here's hydrostasy. Let's just find this pressure, plug it into this equation. So here we go. So we don't have a vertical derivative. This is a horizontal equation, so we have only horizontal derivatives of pressure here. So it is helpful to take a vertical derivative of both sides. So the vertical derivative of f is 0. So the vertical derivative on this side is just dv dz. And then we have d dz of this pressure gradient force term, which is approximately equal to this, this is the Boussinesq approximation. You can do it without if you want, but it's simpler this way. So this then is the gradient of pressure times g over density times g over the background density, which is just the gradient of the buoyancy. But look, this is coming from here. DDZ, the DDZ goes inside, hits the pressure, and that just turns into rho g. That's what we're getting there. So the shear in the geostrophic flow is due to the horizontal gradients in the density, or the horizontal buoyancy gradient. This is how the buoyancy is defined. So you can write this like this, or write this like this, but in either way, it says there's shear in the geostrophic velocity when you have a horizontal gradient in the buoyancy, or a horizontal gradient in the density. So these are the equations that explain this pillows and bricks diagram. There's a horizontal gradient in the buoyancy because it's dense here, low buoyancy, light here, high buoyancy. And so there is a shear in the velocities, just like this says. And if you go through the signs carefully, you'll find that the shear, as written here, is of the right sign. You also, there's this rather complicated diagram from Collins, but it's basically showing barotropic on this side and baroclinic on this side in a 3D visualization, which I did not bother to try to show. And then these little arrows underneath are indicating that because the pressure surfaces are aligned, the geostrophic velocity is uniform in the vertical, and on this side, it's decreasing in the vertical because the pressure surfaces are not aligned. They're starting to decrease as you go down, for the same reason that the hydrostatic pressure here is accumulating a different rate than the hydrostatic pressure is here. If that makes sense. So I said that oceanographers sometimes use barotropic colloquially. What they normally mean is constant with depth. They don't mean the specific definition of barotropic, which is that the density is a function of pressure alone. But because the flow field is uniform with depth in that, people often get loose, and instead of saying constant in the vertical, they just say barotropic. So you might find that in some of the writings you're reading. Okay, so that's enough. We have a thermal wind shear. We have a surface pressure field that's set up by the Ekman flow. We have a thermal wind shear that's set up by the depression in the pycnocline, which gives us a more quiescent deep flow near the level of no motion, which isn't a real thing, but it's sort of a real thing. The end. All right, that's it. We just have one more review of balances, but I'm not going to do that again. We will meet next Tuesday in person, and